really lucky to have online, hoping that Royal Society of Technology will work well. Dr. Dan Sinars from the Sandia National Labs in the US. Dr. Sinars is the Director of Pulse Power Sciences Center, best known for the VZ facility. He's also the Sandia Executive for Inertial Confinement Fusion and other programs of the National Nuclear Safety Administration. He got his PhD in Cornell in 2001, and he's made many, many contributions to high energy density science. He's got more than 130 publications. And as a result of that, in 2007, he got an IEEE Early Achievement Award. In 2011, the Department for Energy honored him with an Early Career Award and also a Presidential Early Career Award. He's a fellow of the American Physical Society, and in 2022, he was honored again with the Ernest Orlando Lawrence Award, which is one of the US government's most prestigious awards for research. So if I can introduce Dan. Dan, are you online?
Yes, can you hear me?
Yes, that sounds good. Take it away.
Excellent. So I was asked to talk about the Z Fundamental Science Program and explain how we use the Z machine to support academic research as a potential analogy for what you might be able to do on the M4 machine. And so as stated, I'm the director of the Pulse Power Sciences Center. I also wear a program management hat. I'm the program executive for Sandia for the Inertial Confinement Fusion and Assessment Science programs. So Sandia is the home of three of the world's biggest pulse power machines, all built in the 1980s. And the emphasis, of course, has been on survivability and fusion research, and so not necessarily built for academic machines, as someone said earlier. The journey started with the Particle Beam Fusion Accelerator 1 machine built in 1980, and back then Sandia was focused on using light ion beams as a fusion driver. That was successful, and they wound up building PBFA2, and that's actually going to be what becomes the Z machine later on. And that conversion from PBFA2 to Z happened in 1996. The PBFA1 facility was actually converted into the Saturn machine, which still exists today, and we use it routinely. And then the third machine is the Hermes machine. So the point of this is that we do a lot of pulse power at the very large laboratory scales at Sandia. And just to give you a sense for the physical size, the Z machine is that large building in the middle. Saturn is over to the upper left, and then the Hermes facility is not even on the screen here. So we do quite a lot of pulse power. We also do gas gun facilities and a smaller scale pulse power machines that help us scale things up to the larger machine. So Z delivers 80 terawatts and about 6 megajoules of electrical energy to the center section. And Nick covered some of this before. It starts with the energy stored in the Marx capacitor banks. So we store about 22 million joules of energy in the Marx banks. And then we discharge that energy radially inward into the pulse forming sections. And here's where the Z machine design differs from the M4. So we have intermediate storage capacitors just like the M4, but then we go into additional pulse compression stages. And all that energy then gets delivered to the center section where it gets translated to a load at the very center. So if you look at what we're doing in terms of power and time, the energy coming out of the Marx generators comes out in about 1.5 microseconds. Because of the high inductance of the Marx banks. And the purpose of the pulse forming sections is to steepen up the energy in time and cram it into a shorter period of time, which increases the power. So that what you get out of the intermediate storage capacitors is about a 300 nanosecond rise time, and what you get out of the pulse forming sections is about a 100 nanosecond rise time. And this could be important later as we think about machine designs, because we can actually short out the pulse forming storage section and get the energy straight out of the intermediate storage capacitor design, and that becomes actually a very robust 300 nanosecond driver. The other thing we can do is there's 36 of these modules, and they can be independently laser triggered to fire at different times, and that allows us to actually stretch this pulse out over up to a microsecond in pulse length. So the Z machine has been optimized to be quite versatile in terms of pulse shapes, and we can do a wide range of physics that is enabled by that. So all that energy and power goes to a target that's shown at the very center of the machine. You can stick a wide range of targets here. So what I'm showing is one of our inertial confinement fusion targets with external magnetic field coils, very complicated setup. But one of the beauties of pulse power is you can stick a lot of different targets at the very center of the machine. And as I'll show you later, right, we are blowing up the center of the machine, so you can redesign all this hardware every time. So the energy of several megajoules is the energy of a couple sticks of dynamite, so that we literally are blowing up the very center of the machine each and every shot. And so we have to then unload this, clean it all up, and do it all over again. So we can do that about once per day for a typical shot. And in a normal year, we get about 150 shots per year. Some of the shots we do, such as our plutonium experiments, we spend a lot of time. We have a special containment vessel to contain all the debris, and those take us several days to execute, which is why we don't get the 250 shots per year. So this gives you a sense for the scale size. What we're trying to do is very similar to what many people do on laser facilities. So we get current. If you deliver the 26 megaamps nominal number for Z to a 1 millimeter radius, you'd get a pressure on the cylinder of about 100 megabars, as shown in the upper left. And if you think about the ablation pressure on a NIF capsule driven by the X-ray radiation, the ablation pressure is, I think, about 140 megabars. So we're able to create drive pressures very comparable to what you can do on a laser facility, but it's happening over different time scales on different size scales. So with that 100 megabars, you can push on samples and reach drive pressures obviously less than the drive pressure of the machine. And that's very relevant for planetary astrophysics. So for example, the pressure of the center of Jupiter is estimated to be about 30 megabars. And a lot of planetary science is in the 1 to 10 megabars type of range. For the extreme goals of inertial confinement fusion, however, you need to get to 100 gigabars is kind of the threshold for getting to fusion reactions and run ignition or propagating burn. And so there, your drive pressure can't directly compress the fusion fuel and hold it at those conditions. So instead, what you do is you use that drive pressure to accelerate samples to high velocity. And then those, especially in a convergent geometry, high velocity things stagnate. And when they stagnate, they can get to very high pressures briefly. And then its own pressure will cause it to fly apart. So the inertial and inertial confinement fusion is to try to get enough fusion reactions happen before its own pressure self-disassembles that plasma. So pulse power is exquisitely suited for a wide range of high energy density science. Our Z machine, we believe, is ideal for megabar class materials experiments. We can compress solids, liquids, and even gases. And we can, as I noted earlier, generate conditions found in the interiors of gas giants or in super Earths or other exoplanets. And so a lot of our fundamental science proposals are for material science because of the things that we can do on the Z machine. As Sergei Lebedev noted, the Z machine also can be an excellent X-ray source. So we can produce megajoules of X-rays, and we use that to look at the effects of radiation on materials and looking for opacity or things like that, or studying the fundamental properties of matter. And what I like to say is everything we know about the universe outside of Earth is from light from a distant object coming to the Earth that we measure. And we make a lot of inferences of what's at the other end of that light source based on models. And so the opportunity for laboratory science is to create plasmas that are well diagnosed in the laboratory. You can directly diagnose the plasma conditions, then look at what you're getting out of that and use that to benchmark models. And so a lot of our fundamental science proposals are doing essentially that. And particularly in terms of using spectroscopy, plasma conditioning, line broadening. Again, these are all models that are used to benchmark the light that's coming to Earth from distant objects. And we do a lot of strong integration between experiments, theory, and simulations, and that'll be an important theme. Sergei Lebedev noted earlier, if you're going to do a very well-diagnosed HED experiment, it typically starts with a very well-diagnosed 3D simulation of some kind. So I'm not going to be able to go into a huge amount of detail on the different experiments. We did publish a review paper in July 2020 in Physics of Plasmas. So if you want a lot of the details of what I just talked about at a very high level, you can see the review paper noted below. So as I mentioned, we can stick very different loads onto the end of the Z machine. And so in inertial confinement fusion, we typically have cylindrical targets. And I'm not going to go into a lot of detail here, but we drive current there. You get a compressive J cross B force that pinches this target down to the axis. It can be very complicated with external magnetic field coils. And again, you're going to put a unique set of hardware in each and every shot. So different fusion experiment, you can put a different hardware set in there. Material properties, instead of using a convergent geometry where you're going to pinch things down, you're going to use typically a divergent geometry. So the two classes that we show on the left is what we call a flyer plate experiment. The current flows through a very small vertical gap. You get a pressure that accelerates a thin sheet of metal called a flyer plate to high velocities. We've achieved up to 40 kilometers per second on Z. That flyer plate will slam into the sample and create a strong shock in the material. And then you can follow the Hugoniot loading path of the material and study how the sample responds. Alternatively, as I mentioned, we can fire the 36 switches on Z at different times and tailor the pulse shape. What that allows us to do is quasi-isentropic compression, where we're going to take the current and we're going to directly use the current to compress the sample. And when we do that, we can drive the sample without shocking it to very, very high pressures by having a very low foot and then a rapidly rising current pulse. And that's sort of enabled by some magic physics where the shock wave outdistances the magnetic diffusion wave. And that allows us to look at sample and material response directly to the pressure wave without having to deal with any of the complicated magnetic physics. So we wind up doing both of these types of experiments. It makes Z very versatile for studying different loading paths. And you can actually combine these two. We've actually done experiments where you take a flyer plate, lightly shock something to raise its temperature, and then you ramp compress it the rest of the way, and you can follow a different path altogether through the loading space. And then finally, there's the radiation sources where we have different types of loads showing you what we're doing. In this case, it's a wire array. So as I mentioned before, you're getting to extreme temperatures and pressures. You need to run the current through the wire array. You're going to radially compress this thing. It's going to rapidly get to high pressures and temperatures that are going to emit copious amounts of X-rays in this example. And we can use that, as I've shown in the picture here, we can put various test objects around the load and take advantage of the X-rays coming out and look at the response of different things to the X-ray flux that's coming from the machine. So the majority of the research on Z is use-inspired. So if you think about Pasteur's quadrant, you want high novelty, or in this case, high mission needs. And so most of what we do is what we call use-inspired research, where we have an application, but we're going to do some fundamental science that we can share with peer review and publish it and get lots of feedback. And then we'll do the more applied stuff, which tends to be more expensive. So you're typically not as novel. You want to buy down the novelty, reduce the expense, and then do the highly applied research. Being a nuclear weapons laboratory, some of our research is not publishable. It's classified. So not all the applied research is out there in the open literature, which again is a key reason for why we like to work with academics, because they help peer review a lot of what we do. So if I make an example, we might measure the opacity of an unclassified material, work with our colleagues in the academic community, peer review it, make sure that we're doing it well, and then we'll go around and measure the opacity of something that we wouldn't publish in the open literature. But we have much more confidence in the measurements we're making because we're doing it and peer reviewing all the processes and techniques. So the Z Fundamental Science program sits completely into basic research where you don't require any specific application for that. And that while that's a small fraction of the shots on Z, it's actually a very important fraction, and we get a lot out of that relationship. So we started our Z Fundamental Science program in 2010, and it's a path for universities and industry to collaborate with Sandia. We've been running it for about 12 years. We've averaged about 8.5% of the shots on Z, or 141 experiments dedicated to this program. And we often allow access not just to the Z machine through this program, but through some of our subsidiary platforms, such as the DICE gas guns, or the Thor Pulse Power Machine, which we use to scale up materials experiments in particular up to the Z machine conditions. Huge impact of all these experiments. Lots of high profile publications have come out of them, Science, Nature, blah, blah, blah. And so we're very proud of it. We're actually the senior scientist running this program for us, Marcus Knudsen. I've asked him to put together a report summarizing the impact of this program. He's made a lot of progress on it. We can share that later when it's available. But it's been very impactful, lots of publications. The way this runs, and I think Nick said this earlier, the NNSA allows us to use this e-machine for about up to 10% per year for the fundamental science program. And this is important because the NNSA is basically paying for the operation of the machine, which includes the load hardware and just the operations folks. So we're not looking for full cost recovery of the cost of doing an experiment on Z. Z is not a user facility. It's not easy to use for external folks. So our proposals require that people couple with a local Sandia scientist, and that helps them be successful, work with our load hardware engineers and things like that. We do require that external researchers support themselves, so we're not paying for any students or professors through this program. They have to have their own research grant that funds them to do the research, and then what the NNSA will pay for is the operation of the machine. We started with every other year calls. We've moved more recently to an annual call process, and to support this, we do a summer workshop every year. And one key aspect of this is that we, Sandia, are not picking the winners and losers. As a national laboratory, we're required to be objective and independent, so we rely on an external peer review process that peer reviews proposals that come in from the outside, judges their quality, and then makes recommendations to us as whether they're a good quality or a good match. We do look at it from an execution point of view. Is this a proposal that our facility can execute well? But otherwise, we rely on peer review for a large part of the decision making. So a key aspect of this that has really been helpful is this workshop that we have every year. We've had an annual workshop every year since 2010. It has a combination of plenary sessions and breakout sessions. The plenary sessions are from folks like me giving an overview on here's where the Z machine is, here's our diagnostic capabilities, here's what we're doing. And then we do breakout sessions on various topical areas that allow the researchers to share with each other what they're doing, and also to meet and greet the scientists at Sandia and make that partnership happen wherever it needs to happen. We specifically encourage students to attend, and so NNSA actually subsidizes this through the NNSA academic programs and provides travel support for 20 to 25 students each year. And then, for example, to give you some numbers, the 2022 workshop was done in person this summer. We had 124 attendees in person, 56 not from Sandia. And we also had a few people attending virtually, so a hybrid meeting just like this one. As I said, we've gone to an annual call for proposals. The proposals are for 2-year periods, so we do a call every year, but you get a 2-year award if you're awarded shots. And as I said, we do facility review for how, can we execute it? Is it safe to execute? Looking at the diagnostics, do we have the diagnostics to make the measurements that they want? We have a scientific external peer review, and then we make decisions. So we are about to announce in just a couple of weeks the decisions for the shots for the next 2-year award period. This has been a steady growth in academic participation, and you can see that we're currently at about 21 students, and I think it's 7 postdocs. And so this has been incredibly successful in terms of getting academic engagements. And over the 12 years we've been operating, we've produced 21 PhDs on various projects associated with this. So that's about an average of about 2 per year. But as you can see from these numbers, I expect this rate to be increasing because we have a lot more students today than we did when we started this 12 years ago. And from an NNSA perspective, why might they care to fund this? Because, hey, we've got 6 former students or postdocs still at an NNSA lab today from this program. So that's a big success. So again, just to give you a couple of examples to what your appetite for the things you can do, you've heard some great examples from Sergey Lebedev. So in this example, we're going to use a wire array, this very large object, about 4 centimeters in diameter. You're going to run the current of the Z machine very reliably, about 26 megaamps of current, and that generates its own magnetic field, and then you get a J-cross B force that compresses this radially inward, and you get a copious amounts of X-rays. So in this case, about 1.6 megajoules of X-rays. This is a very reproducible source. I produced some references down below. It was actually originally developed as an X-ray source for inertial confinement fusion research, but it turns out to be a very versatile platform for making soft X-rays to drive a wide range of X-ray experiments as well. So we have many different platforms that use this today. I'll walk you through 3 examples. So the first example here is we can put a sample on the top that gets exposed to very high fluxes of X-rays, and consequently we can get to very high temperatures and start with a solid density sample and get it to high temperatures very quickly while maintaining the density very high. This is very relevant to solar astrophysics, where you're trying to understand what's happening with the convection boundary of the sun. I don't have time to really go into the detail of this, but Stephanie Hansen's talk later this morning or afternoon for you will show more details of what we're doing with this plasma. This is very exciting work. It led to the 2016 Dawson Award from the American Physical Society, and we're still doing a lot of active research on this opacity platform. Very exciting. You can also look at it to use accretion disks. So here we're using X-rays coming out from the side of this. You're putting a thin silicon foil, and you're using that radiation to ionize the silicon radiation. And again, that models some of the things that might happen in the accretion disk of a star. And you can see very different plasma conditions being created. Or you can create a gas cell and use that again to look at create different conditions in the hydrogen gas. And hydrogen and helium are key components of what we see in white dwarf stars and the photosphere of the white dwarf star. And people have models for what they're interpreting, what the conditions are at the white dwarf star. And we are currently trying to benchmark those models for hydrogen and helium. What's really interesting is we're getting different results than the typical models show. And so the group led by Don Winchett at UT Austin has been studying this for a few years now and trying to really benchmark the models. And then from that, back up what that has to say about white dwarf stars. If you know a lot about laboratory astrophysics, white dwarf stars are sort of the standard candle for understanding the age of the universe. So these measurements are going to directly influence our understanding of how old the universe is, because the conditions of white dwarf stars are directly used in the inference of the age of the universe. And then Sergei Lebedev showed this picture earlier. We recently used 2 wire arrays to do this magnetic reconnection experiment. Since he covered in detail, I won't say a whole lot. Again, a unique feature of Z is we have a lot of energy available to us. We can drive very large plasmas and get these things to extreme conditions. And so this is really exciting. This is also unique. Most of the plasma platforms that we're using for fundamental science experiments on Z are platforms that Sandia had already developed that were modified or optimized in some way for the academic use. This is the rare counterexample where we made a new platform specifically for a fundamental science experiment. There is no NNSA application for quite this work. There's some risk that comes with that. Will it work? And as Sergei noted, it was a huge achievement for this thing to work on the first shot, but it also took a lot of effort. So this is more exceptional than the norm. So let me walk you through an example of a materials experiment. And so in this particular example, we're looking at bridgmanite. So people are very interested from a planetary science in all these different composite materials that are relevant to different types of planets that might form. And what we're very interested in is things that are Earth-like in this example. So bridgmanite is a polymorph of magnesium silicon dioxide or trioxide. And so what we did on the Z machine, I won't again have time to go through all the details, but we worked with the academic partner. They provided us with a very high density solid sample of this from former bridgmanite. And what we were able to do, in contrast to what had previously been done in laser experiments, was start with a solid and then directly measure the onset of melting. And we were able to measure exactly where that melt temperature was over a series of Z experiments with the academic partners and put bounds on the melting phase and at what temperature does it melt and what pressures. And it turns out that it was very high melt temperature at high pressures. And what that does then is it puts constraints on what you might find in these planetary. So if you've been following the news, right, finding all these super Earths or planets orbiting different stars based on these oscillations and wobbles that you see in the light data coming from them. And what people are really interested in doing is finding Earth-like planets. And so you can know things like the radius of the planet relative to the radius of the Earth. And you can also, based on different measurements, estimate the size of the planet relative to the size of the Earth. And that tells you something about the density of the planet. And what we're finding, what we can use this data for is to look for things that have similar densities to the Earth, which then implies that they may have similar ratios of the materials as we do on our planet. And what is important about that is then it increases the likelihood that there is a magnetic field on that planet. And so there's some thought that you need to have a magnetic field on a planet in order to have a chance of life being on that planet, because the magnetosphere of the planet helps shield us from the solar radiation and solar particles streaming from the sun. So very interesting work. Again, I don't have time to go into a lot of the rich detail here, But the theme here is making fundamental measurements of material properties or X-ray properties or response to radiation transport. I spoke to you about the M4. Sandia is also interested in a bigger pulse power machine, and we're presently working with the NNSA and refining the requirements for what that machine will ultimately be. The nickname for the project is Next Generation Pulse Power. When it's done, it'll be some machine that will not be named this. I know the name is kind of awkward. So that machine will full stop be the world's most powerful warm X-ray source. NIF and Z are actually very comparable. We both have a couple megajoules to play with, as Sergey noted. But this machine will have far more energy, as I'll show you in the next slide. And so it will be a very powerful source of warm X-rays. We're targeting this to support fusion yields up to of order 100 megajoules, maybe 200 megajoules. We anticipate providing advanced capability for high energy density physics, such as dynamic materials research. And just the process of building it will help us advance the state of the art for fast pulse power technology. So we launched on that journey last September of last year. We anticipate finalizing the mission need and requirements with the NNSA within the year. And that will set us up for going through various analysis of alternative studies and things like that, so that the main project funding would begin in 2026. So one advantage that Nick has is, as long as he can convince the investors that it's worth doing, he can probably go a lot faster than the NNSA will. So we're very excited to potentially collaborate with First Light Fusion and maybe go more quickly than we could in the absence of collaboration between the two of us. So we've been doing a lot of different machine designs. The traditional ways, you start with a load, you work your way back outward and piece of paper. We've actually automated a lot of this with machine designs. You can do all sorts of optimization that way. Currently, we're at over 30,000 unique designs for NGPP. We're storing all these in a database so that as we refine what types of science we'd like to do with it, we can go in the database and figure out which optimized machine can do this. So I'm just showing you one example. It's not to say that this is the definitive machine design that we're going to do. In this example, it's a traditional Marx generator. It has an intermediate storage capacitor, pulse forming, and then MRTLs, as Nick said, and then a center section. So a sense of scale, Z is about 108 feet in diameter. This would be about 3 times that. Marxes, we go from about 36 Marx modules to about 75. Capacitors, about 2,000 capacitors to 13,500 capacitors. And this is important because we will have to partner with private industry to build all these capacitors. If GA, General Atomics, didn't drop any of its customers, for example, it would take them 15 years to build this number of capacitors. That's just to say that they'd have to increase their production if we were going to use them, and they're one of the larger capacitor production firms in the world. So the power that delivered to the load, instead of 80 terawatts and 6 megajoules delivered to the vacuum insulator section of Z, we would be delivering something like 600 terawatts or 50 megajoules. You can also look at different pulse power architectures. I'm not saying that the Marx generator is the only design, and we are looking at different pulse power architectures. This is, again, just to give you a flavor for the scale that we're looking for. So what we're trying to do then is we're putting a lot of the risk on the pulse power machine in terms of energy to target and the peak power to target. So I think of the energy as the strength that you have. The peak power is power. And what you're ultimately trying to do from a fusion perspective is to create high energy density conditions in the target. And this is done through control. So in the NGPP design, we're going for high energy and high peak powers and allowing us to do a wide range of targets at the end. The advantage of the amplifier technique is that it perhaps allows you to reduce the power requirements because you're going to put more of the, you're going to transfer a lot of the physics to the target itself and make the target do more of the work to get to the high energy density conditions. So this just gets you a different sense of the trade-offs that you're looking for. Having more energy allows you to have larger targets. So for example, in the magnetic reconnection experiments that Sergey showed on Z, why go to Z? You can get a larger plasma, you can get to more extreme temperatures and densities, and that actually makes it easier to diagnose and a lot of stuff like that. If you have larger targets, you can also get higher yield more easily. You don't need to do as exquisite pulse shaping as someone talked about earlier. You can get away with a lot because you have more energy available. So the 4-step pulse shape on the National Ignition Facility, for example, is required because of the relatively small amount of energy that's available at that scale. If you can get more energy to the target, you can get away with fewer shocks or fewer pulse shaping. And then if you change the target to be like a revolver style design, you're putting more of the shock tailoring into this target itself. And then from a materials perspective, it's very important. The larger energy of Z allows us to shoot very large samples. And large is relative to the grain size of the material. So our sample sizes are much larger than the grain size of the material. So if the grain sizes are playing a role in strength, for example, we're going to inherently capture that in the experiments that we do on Z. Peak power can be very important if you need a lot of energy radiated in a short time. So for radiation sources, peak power is actually very helpful because the radiation is a loss, and electron heat conductivity is your other barrier. So those are the two things you're typically fighting in fusion. And so if your driver can get that power and energy to the target very quickly, as in the National Ignition Facility, you can do a lot. If you're trying to ignite, you really do need to get to high pressures, 100 to 200 gigabars. And so that's really why we were building this larger pulse power machine, is to get a chance for doing that. It's not really a fair comparison to compare maglev targets to what they're doing on the National Ignition Facility. Maglev by design is using magnetization to reduce the fusion requirements. So this 2 gigabars is not really meant to be directly comparable to here. I need to work on this table a little bit. So I think there's a lot of options for fundamental science on a future facility. Imagine what you would do with a 10 megajoule X-ray source, or higher temperature plasmas for laboratory astrophysics, such as opacity, larger sample plasma sizes due to more energy, things like that. So I think there's huge opportunity for fundamental science on a future facility, be it the M4 or an NGPP. So last slide, closing thoughts. Pulse power machine design, we have found the ability to tailor the current pulse from 100 to 1000 nanoseconds to be very versatile. It allows us to do a wide range of dynamic materials experiments in particular, including the quasi-isotropic compression experiments that I talked about, which complement what you can do in shock and Hugonio experiments. And the way we do this is through the ability to trigger different modules at different times. From a pulse power design perspective, we think Marx-based architectures may be better suited for this than some of the advanced pulse power designs that have intrinsically short pulse architectures, where you're going to extract the energy directly from your energy storage in 100 nanoseconds. And the reason for that is that back reflections are very challenging. If you're going to extend the pulse shape, then the energy goes to the very center of the machine. It'll back reflect and get to other parts of the machine which haven't yet been triggered, and you need them to not be triggered by that back reflection. Diagnostics, both the previous speakers spoke about this. The philosopher Ludwig Wittgenstein used to say, the limits of your language is the limits of your world. The analogy here is the limits of your measurements defines the limits of your science. You might do the greatest experiment in the world. If you don't have a great diagnostic to measure that experiment, it doesn't matter. You have no idea what happened. So for perspective, we've invested about $10 to $15 million annually on diagnostics on Z over the last decade. NIF has also invested about $40 to $50 million of diagnostic investments annually. This is a big deal, right? We spend a lot of money on diagnostics to make cutting edge measurements at extreme conditions. Now, the good news is I think we can leverage a lot of that investment on the M4. And so I'm not saying that this needs to be the budget for the M4 to do diagnostic science. It's just to say diagnostics are important, and it takes a lot of effort to make them work well. Platforms, as I said earlier, it's rare for Z fundamental science proposals to develop a new platform. Mars is the shining exception. It's much more often that it'll utilize an existing programmatic platform and adapt it to their specific application. So this is perhaps going to be a challenge if the M4, the main application is just diffusion experiments. It's going to put a lot more emphasis on the fundamental science program or academic access program to develop those platforms. And then finally, modeling and simulations. They're critical not just for experimental design, but often you get this complex data from the measurements you're making, and you rely on simulation to tell you what that plasma conditions are based on the data you're measuring. So it's not just experimental design in a forward sense, but also post-processing analysis is often requires experiments. And in some sense, if you don't have great design tools, it's going to limit the boldness of what you think you can take on. So the people that are really pushing the envelope, like the Mars platform, are able to do that because they have these great simulation tools that allow us to be bold, if you will. So just a high-level overview. Didn't have time to do a lot of science there, but to give you a flavor for what our academic access program is like. And with that, I'll stop sharing and take any questions.
Thank you very much, Dan. That was a really incredible skate through lots and sorts of issues, everything from using such machines to benchmark and validate areas like astrophysics that you couldn't do any other way, Your description of how you interact with the academic community was really fascinating, both to ultimately increase your own capability, but also the use of academic collaboration to help your own classified work. The supply chain question is really interesting, on how much you spend a year on diagnostics, for example, both to keep going and to improve. So lots of areas for food for thought for First Light Fusion there, I imagine. Questions for Dan? In the back.
Justin Walk from the University of Oxford. Thanks for that very interesting talk. I was interested on your last.
So I can't hear very well. I don't know if they're holding the microphone close to their mouth.
Justin Walk from the University of Oxford. Thanks for that very interesting talk. I was looking at your slides on how you want to get high gain, and you were saying that that's probably a maglev type concept. So how would you compare that with double shell or revolver type designs, and why have you gone down that route?
So perhaps the moderator can repeat the question.
Would you like to come here and ask a question here? I think that's probably the easiest thing.
Yeah, I'm not sure that microphone is working. I had a hard time hearing Simon Bland. It seemed to work early in the conference, but...
Justin Walk from the University of Oxford. I was interested in your sort of high gain design, and you mentioned maglev, and could you comment on why you would be going down the maglev type design rather than a, say, double shell volume revolver type design?
So I think we can do everything. And in fact, we have multiple fusion concepts that we're pursuing. I share maglev because that's the primary thing that we publish in the open literature with people. We actually did magnetic indirect drive, where we made X-ray sources to drive capsules for over the first 15 years of the Z machine. And we stopped doing it, not because it was a bad idea, but because all the risk was really on the target capsule physics, which the National Ignition Facility was coming online in 2010 to study. So the Z machine, we don't have enough energy to really drive large capsules today. So we could get capsules only up to about less than 100 EV temperatures. So it's really only interesting for the pre-pulse of what you can get on the NIF. The NGPP will be of a scale that you could drive, use magnetic indirect drive to drive things. I would actually love it if we would partner with academic or other national laboratories to do more magnetic indirect drive designs. We have a small team here at Sandia, so we're mostly focused on the magnetic direct drive like maglev concepts, where we use the magnetic field to directly pinch to plasmas. So all this is to say, yes, we should look at things like revolver on Z, whether it be from an X-ray drive or an amplifier or things like that. These machines are versatile, and we can study a wide range of target concepts.
Thank you. Other questions for Dan? Just an inexpert question from me, if you'll allow. I noticed when your first couple of slides, one of the machines that you built was an upgrade from the previous one. How much is, for your new facility, are you even thinking now of what it will be like in 20 years' time and its upgradability? Is that a design feature that Nick needs to be thinking about?
Yeah, it's a great question. So we're still in the early stages of the design, and in some sense, the question is, how big of a machine will we be able to build from the NNSA? And flexibility and upgradability may require more money up front in order to leave space for that. So different flavors, for example, you could imagine building a machine that had fewer Marx modules, but leaving space for additional Marxes to go in. But that would then require that you build a bigger facility than you might initially need, so you have space for those Marx modules. I think things like that are eminently doable. And it's really going to be a design question from the NNSA, like how much do they want to just build up at the beginning versus upgrade later. Other things we've looked at is whether could you stack, have multiple layers and stack them up. That winds up becoming challenging from an operations point of view. If you want to get to the bottom layer, you got to remove the top layer or something like that. So we're definitely looking at upgradability as an option, but it's obviously simpler if you just build a machine you want right from the get-go. And
also on your supply chain, how much of it is completely dedicated to you and how much of it has a much bigger market?
So we have a robust supply chain that we use local machine shop. For example, all that load hardware that gets blown up every shot, We've got a robust supply chain that's all local to Albuquerque that we use to build and manufacture a lot of the load hardware. The targets are mostly made by General Atomics, which supplies all the targets for the inertial confinement fusion program overall. So shots on NIF, on Omega, and on Z all use targets fabricated by General Atomics. So that is by no means captive to Sandia, and that allows us to share some of the resources. It's a little bit more efficient because we don't use all the tools they need for everything at 100% capacity, and then they use the other capacity for the other facilities as well. We don't build machines that often, right? So capacitors, things like that, we are by no means a captive market, and NGPP in particular, and if we build both NGPP and M4, that's going to be a huge shock to the capacitor production market, and I think there's a lot of opportunity for industry to step in and build things. It's very analogous to what they did for the National Ignition Facility and the laser megajoule in France. They had to partner with two different companies to build production lines to build all the laser glass needed in those facilities. Those companies built all the laser glass and then promptly stood down the production lines. There may be some analogy here with capacitors. Right. So Sandia is a design laboratory. We're not industry. We don't build things except in very rare cases. So we're definitely going to also be looking to partner with industry to build this machine and possibly help us with some of the design.
Thank you. Any final questions for Dan before lunch? One at the back there.
Hi Dan, can you hear me okay?
Yes.
Cool. It's Jack Halliday from Imperial College, and I'm just curious, I think about the same question that Jerry asked initially, which comes down to rise time proposed for M4, and in particular for, say, the wire array loads or the maglev type loads. How important is this rise time question for the new machine?
Yeah, I think it's mainly important if you care about X-ray sources. So, people have looked at longer pulse machines such as gas puff sources and things like that. And what you find is just generally, if you're longer than 300 nanoseconds, you're just not going to get a very high power X-ray source coming out of it. And frankly, the experience that we had is the shorter the pulse, the better. 100 nanoseconds is a practical lower limit to the pulse length if you want high voltage. So if you really want robust and powerful X-ray sources, high power X-ray sources, not necessarily high energy, you're going to need that shorter pulse shape closer to 100 nanoseconds, definitely no longer than 300 nanoseconds. And I think that's consistent with what Sergey said earlier. Okay.
Thank you so much. Dan, thank you so much for joining us from Sandia and for your contribution to the day for us. That's it for now. We are running a little bit late, so if you lunch still got 45 minutes. It was plenty of time, I hope. So back in this room at 1:15. Thank you.
Thank you.